biomedical image processing course. In this module, we will see extension of the standard approach which normally formed while acquiring the image and capturing their various features. The standard approach for automated microaneurysm detection has been embraced by a number of groups, including the University of Aberdeen, the research group established by the author at the University of Waikato, New Zealand, and by other researchers also. Hepwell and his group of Aberdeen University modified the automated microaneurysm detector of the Cree and his group to work on red-free images of 1024 by 1024 pixel resolution of 50-degree field of view retina either centered on the macula or nasal of the optic disc against a testing set of 62 images containing total 88 microaneurysms. In those images that broadly reflected the level of retinopathy expected in an eye screening population. The automated microaneurysm detector achieved 43% sensitivity with 0.11 false positives per image for detecting and correcting locating a microaneurysm. This less sensitive operating point was chosen as being more suitable for eye screening as only one microaneurysm per image needs to be detected to identify the retinopathy is appear or suffering by that subject or not. The poor ability to detect microaneurysm in red-free images compared to using fluorescent angiography seems to have diversely affected the overall ability of the automated microaneurysm detector in the study which was currently performed. In an extensive trial using 3783 directly digitized red-free images from the diabetic eye screening program, the automated microaneurysm detector achieved a sensitivity of 81% at a specificity of 93% for detecting images that contain a lesion called microaneurysm. By using this method, it is possible to get sensitivity of 85% at a specificity of 76% for detecting the subject with retinopathy. It was concluded that the automated microaneurysm detector would be useful in a screening context to remove half the images that contain no retinopathy, thus would reduce the load of subsequent manual screening method. The Aberdeen automated microaneurysm detector in conjunction with an automated exudate detector was also reported in a comparative evaluation of digital imaging system, retinal photography, optometrics examination and automated retinopathy detection process. The automated detection again used red-free images of 1024 by 1024 pixel resolution of 50-degree field of view, that is called FOV. A total of 586 participants, of which 157 had retinopathy were included. The automated retinopathy detector achieves 83% sensitivity at a specificity of 71% for detecting any type of retinopathy during screening programs. This compares to 83% sensitivity at 79% specificity for manual detection of retinopathy from the digital red-free images, and 89% sensitivity at 89% specificity for manual detection process of the retinopathy from color slides. Olson and his group conclude that the automated retinopathy detection is not yet ready for sole use as the screening mechanism, but could form an important adjunct to reduce the workload of the manual screening process, which is tedious and time consuming. A number of other groups have used the standard approach as a starting point for developing automated microaneurysm detector systems. Mendock and their researcher implement the standard approach for detecting microaneurysm in fluorescent angiographic images, but only reports result of testing on one image. Acha and Serrano use the pre-processing of Mendock and their groups and extended the classifier to include features that are based on the correction and correlation of various safe filters with the candidate. On 5 angiographic images with a mean of 100 microaneurysm per image, they achieved 82% sensitivity with 3.3 false positive per image. Serrano and his group further enhanced the image processing strategy by using the errors of linear prediction method coefficients as a means of adaptively thresholding the match filtered image to generate seed points, and which can be further utilized for region growing approach. The classifier appears to be essentially the same as Acha and Serrano. On 11 angiographic images containing a total of 711 microaneurysm, they reported a sensitivity of 91% of detecting microaneurysm at 7 false positive per images. And his group report on the detection of microaneurysm in low resolution color retinal images. The green plane of the color image is used for pre-processing and detection of all interested desired lesions. The removal of blood vessel in the Toffat stage is improved with the use of morphological reconstruction. Notably, they dispense with the match filtering stage and threshold the Toffat processed image to generate seed points of the region growing technique. Basic shape features as well as the hue of candidates as determined from the full color information is used in classification. A preliminary test on 46 images of healthy and diseased retina achieved around 90% sensitivity at 80% specificity for detecting presence of microaneurysm in the diseased retinal images. Lalonde and his group used this microaneurysm detector in their RedSoft Plus retinal analysis software. Raman and his group in a study on the effect of image resolution on automated diabetic retinopathy detection used and microaneurysm detector based on standard approach. A Toffat transform is used to isolate small object in the shaped corrected image and match filtering with a Gaussian model to detect vessels. Any small objects detected in the top hat that occurs on vessels were removed. A genetic algorithm processes the microaneurysm detection from 345-degree field of view of an eye to arrive at a report on the presence of diabetic retinopathy for the eye. Color retinal images are used in the study, but no mention is made of how the color information is used by them. On high resolution images, 10 diabetic retinopathy, 8 no diabetic retinopathy, that is NDR, a sensitivity of 90% at a specificity of around 88% was achieved for detecting retinopathy. The resolution of images is not stated other than they are digitized images of 35 mm film of 35-degree field of view using mydriasis, and the images were used for both the training process and the testing process of soft computing. On low resolution images of size 640 by 480 pixel of 45-degree field of view, non-mydriatic direct digitization of 91 subjects with 35 diabetic retinopathy, 56 non-diabetic retinopathy that form an independent test set. A sensitivity of 69% with a specificity of 66% was achieved for detecting retinopathy. This reinforces the conclusion of Spencer and his group that digitization at approximately quarter megapixel resolution is insufficient for automated detection of microaneurysm. Nengemer and his group find that standard approach for segmenting candidates fails to segment all true microaneurysm. Thus, they developed a new method to generate all such desired required candidates, that is based on pixel classification. After said correcting the image, pixel intensities and first and second order Gaussian derivatives at various scale are provided to a k nearest neighbor classifier that produces a probability map for each pixel to be a small red lesions. This is thresholded and filtered to remove vessel segment and object that are too large, leaving the candidates. They test the standard approach and their new pixel based approach for detecting the region of interest for generating the candidates and find that both methods fail to detect 40% of true microaneurysm, but when combined together into a hybrid system, that figure is reduced to 10%. When coupled with the usual region growing and final classification to detect microaneurysm, the hybrid system achieved 100% sensitivity at 87% specificity for detecting the presence of retinopathy in 50 training images. Out of them, 27 were diabetic retinopathy and 23 were non-diabetic retinopathy of size 768 by 576 pixel resolution. The standard approach suffers from other known problems. The region growing applied to delineate candidates can be unreliable if the candidate is on or near a vessel in cluster of microaneurysm or is in a region of unusual background texture. Most research work is based on the standard approach terminate region growing when intensity increases beyond locally determined threshold. If the resulting grown object does not accurately reflect the underlying shape, then the measured features are likely to be inaccurate, resulting in false detection or missed classification of microaneurysm. The other problem is local contrast variation. Microaneurysms can have poor contrast in some part of the image, while background texture has higher contrast in other part of the image. The said correction of retinal image compensate for local contrast variation. Nevertheless, close examination of automated microaneurysm detection results suggest improvement can be made. Fleming and his group address these concerns. The region growing stopping condition is based on mean squared gradient magnitude of the boundary of grown object. They find that this function is maximized when region growing approach is terminated on the boundary of microaneurysm, and its use improve delineation of candidate shape and extent. Fleming and his group measure the background contrast in a local region about each candidate with a watershed algorithm that exclude features such as other microaneurysm and vessels as lesions. The background local contrast is used to normalize the intensity based features measured on the candidate. Features on the boundary of the candidate are measured as well. As a final adjunct vessel are detected in local region about the candidate using an efficient scheme to detect linear structure, and any candidate lying on a vessel is removed. This type of constraint has followed to get the higher accuracy. In an earlier study, Fleming and his group show that the use of their local contrast normalization and the detection of candidates lying on vessel improve sensitivity by about 6% and specificity by about 8% for detecting retinal images containing microaneurysm on a database of 720 good quality retinal images, of which 216 contained microaneurysm. Fleming compared number of local contrast normalization scheme and found that their proposed scheme performed best and gave a useful improvement to detect microaneurysm. The system achieved a sensitivity of 85.4% at 83.1% specificity for detecting images that contain microaneurysm of 1441 images, of which 356 contained microaneurysm lesions. All the above implementation of the standard approach used monochromatic images such as fluorescent angiographic images, red-free images, or green plane only of color retinal images. Microaneurysms are well distinguished in the green plane of color retinal images. Nevertheless, one wonders whether using the full color information, particularly in the final classifier, may provide an edge in sensitivity and or specificity. The problem that global SAID correction does not normalize the contrast of microaneurysm sufficiently has also been described by Hum and Han. They improve local contrast by first applying SAID correction coupled with non-linear contrast enhancing transform to local 120 by 120 pixel blocks of the image that slightly overlap with one another. Candidate microaneurysm, which is small circular object, are found with a Tophet transform, and the area and maximum intensity of the candidate must be greater than locally determined threshold for the candidate to be accepted as microaneurysm lesions. The results were determined on for too few images, 12 images for 6 subjects. For any meaningful comparison to implementation of the standard approach, Walter and the group describe similar approach to local image contrast normalization. Artificial neural network can be another approach and which have been explored for detecting microaneurysm and other lesions in retinal images. Varying approaches ranging from using raw pixel data to substantially processed image data as inputs to neural network have been tried, and by following that machine learning approach they have got a very good detection of the lesions, while Gardner and his group detected lesions and features other than microaneurysm. Their work is notable in that they break the image down into small windows and use the pixel data for the window. After pre-processing with median filter noise suppression as well as the result of the Sobel edge operator as input to a back propagation neural network. This approach is based on philosophy that neural network should be able to recognize the interrelationship between pixel that enables lesions to be detected in those set of images. Camel and his group take a similar approach to detect individual microaneurysm. Unfortunately, the resolution and number of images used in the study were not stated. Thus, one cannot use the result of this particular study for comparison. Morgnati and his group seems to take a similar approach for detecting microaneurysm and other lesions, though they used a pre-processing step to locate maxima, to detect exudate, and minima to detect microaneurysm. With the pixel data in 5 by 5 pixel window about these points as input to the neural network model of soft computing technique. They also apply committee technique to the neural networks. They use images of 512 by 768 pixel, which is insufficient resolution to detect a lesion such as microaneurysm reliably. Error rates ranging from 8.3% to 12.7% are reported for various algorithms to detect microaneurysm in small image segments. The non-standard testing methodology make it hard to compare to other published result of the researcher. The output of image processing operator that aid segmentation such as matched filter and morphological operators like erosion and dilation can be provided as input to the neural network, thus potentially giving the neural network better information to work with. This can be taken to the extreme in which the standard approach can be used to segment candidate microaneurysm and then use a neural network model to classify the candidates as microaneurysm or spurious objects present in the images. This is the approach taken by Frame and his group, in which the final classification stage of the microaneurysm detector of Cree and his group was tested with various classifiers including neural networks. The manually constructed rule-based classifier as used by Cree and his group was found to be best among all the classifier which has been 8 listed out by various researchers. A variety of general purpose operators other than those typified by the standard approach can be used to segment microaneurysm in retinal images. Hong and his group, after said correcting the retinal image, generate an age map of the retinal image with the canny age detector operator, which is one of the most significant age segmentation operator. The idea is to detect an closed circular edge that surrounds a microaneurysm. Edges that are too long or too short to be a microaneurysm, as well as edges weak in intensity are removed from the age map. Edges that resemble small circle are identified and with reference to the green plane of the retinal image. Those that enclose a low intensity region inside the circle are retained as candidate of region of interest called microaneurysm. This still contains some false detection. So intensity and safe features are measured on the candidates and used in classifier to improve specificity. An advantage of this method is that the segmentation algorithm naturally provides the underlying boundary of the microaneurysm without resorting of region growing. Walter and his group note that the Toffet transform of the standard approach tend to detect tortuous vessels as round small object. This is because the linear structuring element fails to fit inside such vessel at any orientation. They overcome this problem by using a morphological bonding box or diameter closing similar to area closing described by Vincent to segment microaneurysm type of lesions currently present in the images. Intensity and safe features are extracted for the candidates and classified with Bayes classifier with kernel density estimation. The system achieved 89% sensitivity at 2.13 false positives per images for detecting microaneurysm in 94 images, 64 by 640 by 480 pixel resolution, 68 diabetic retinopathy and 27 non-diabetic retinopathy images were there, containing a total of 373 microaneurysms in those images. This result compare. They overcome this problem by using a morphological bounding box or diameter closing similar to the area closing described by Vincent to segment microaneurysm type of lesions. Intensity and shape features are extracted for the candidates and classified with Bayes classifier with kernel density estimation. The system achieved 89% sensitivity at 2.13 false positive per images for detecting microaneurysm in 94 images. Out of them, 640 by 480 pixel resolution, 68 were diabetic retinopathy, 26 were non-diabetic retinopathy, containing a total of 373 microaneurysm type of lesions. This result compared favorably with the 3 human graders reported. One may question the low resolution of the images. However, it is to be noted the use of 3 CCD color camera that produces better quality image than the equivalent resolution and typically used 1 CCD camera with Bayer mask. This is a major difference they have in their process of acquiring images. Their database included 995 images with 1280 by 1008 pixel resolution, including both angiographic images and the normal photographs captured by the fundus camera. It is not clear how many images were used for training and how many were used for testing. It is hard to believe that all 995 images were manually segmented by graders, as that is very time intensive task. Now let us summarize. Overall, we have seen in this module extension of standard approach and other approaches to extract the important features called the microaneurysm, because these features may be overlapped with other lesions of the images. Hence, that's why more detail we have come across in this particular module. In next successive module, we will go for general red lesions detection process, and that along with that we will also come across with other methods include for classification too. Thank you very much.